Okay, the ideal gas equation is a really important equation that we deal with a lot, and it obviously is something that you've seen before, but it may have a little bit of a different context and meaning here in this class, okay? And as I mentioned before, the most important thing is that we have to realize when to apply it and when not to apply it, because that's a big mistake students make, okay? And it's kind of obvious, but sometimes when you're in the middle of a test and you're nervous and you're going real fast, things that are obvious become not so obvious. And so I'm going to try to cement them in your mind and say that we typically apply the ideal gas equation to gases, okay? Yeah, I know. We're redoing. Yeah. So we're redoing because it's tape. So so we apply it to gases, okay? And don't apply it to things that are not gases or vapor, in the vapor form, okay? But the most obvious thing that we're going to apply to a lot is air, okay? All right, we're going to apply that to air. And that's pretty much, whenever you see a problem dealing with air as what we call the working fluid, if air is a big part of it, ideal gas is probably going to be there, okay? Whereas, what do we not apply the ideal gas equation to? Well, water. Let's not apply it to water, okay? H2O or steam, okay? None of those, okay? No liquids. No liquids, no solids, please. Okay? None of that, okay? We have tables for steam. Don't apply the ideal gas equation to steam. Now, if you read your book carefully, it will tell you that when steam is superheated, superheated, if it's really, really hot, there's times in which you can kind of get away with applying the ideal gas to steam. Sure, but let's not do it. Let's just say no. No ideal gas with water. No, 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 no. Okay? No. All right? No ideal gas with water. We got tables for that. We don't need to do it. The most likely thing you're going to do is when we apply it to air. Okay, so let's get to the ideal gas equation. Okay, PV equals RT. This form is a little bit different than what you may have seen in your chemistry course. Okay, with your chemistry course, you may have seen a form that says PV equals nRT. You may have seen it like that, and oftentimes the PV equals N. It'll look something like that. Where the volume is total volume, whereas in ours, the volume is specific volume. That's little b there, that's specific volume. And P, of course, is pressure. R is the gas constant, and not to be confused with the universal gas constant, okay? We're not talking about the universal gas constant. Typically, what you're going to do is you're going to look up R for each substance. And actually what it's going to do, it's going to make things a lot easier, okay? And the R that you're going to use by far the most is air, okay? In fact, I usually put it on your formula sheets because it's so much in use. The R for air, the ideal gas constant for air, is 0.287, and that's going to be kilojoules per kilogram K. So I usually put that on your formula sheet because you have it so often, we use it all the time. Okay? So we look up R for each substance, and you do have tabular data for that. If you go to your tables here, and you go to your first thing here, table A2 has ideal gas specific heats and gas constants for air, argon, butane, hydrogen, methane. It even has one for steam, but let's not use it. Propane, oxygen, okay. All right. So there are some R values given in your tables, okay? There's even some here too. A1, gas constants, all sorts of ones here, okay? So that's what makes life easy for us. You don't have to look that up. You don't have to look up you don't have to like memorize R's. You can look them up, okay? Now, by the way, the R, the actual R value comes from the universal gas constant divided by the molar mass. You may remember that a little bit from chemistry, okay? And you can figure out the molar mass, by looking at the composition, H2O and all that kind of stuff. You can say, okay, I got 2 hydrogens, 1 oxygen. You add them up, all that good stuff. So it's not that hard to do. But we don't need to really mess with that, because we'll just look up the R and we'll just directly plug and chug into that formula, okay? And so that's going to make life a lot easier. Now this formula is very powerful though, and we use it a lot, okay? PV equals RT is very powerful, and we're going to use it in a lot of different cases. So what I thought I would do is I have 2 examples of how we could use it, but I'll tell you we're going to use it a bunch, okay? It's going to be really important, but it's going to be important in air, okay, not for water, not for steam. Okay, take a look at this first example here. It says air at atmospheric pressure and temperature of 27 degrees Celsius is expanded from a volume, in case you don't know, that's a volume there, right, because it's meters cubed. That'd be like V1, to a volume, V2, of 0.5 meters cubed, in an isothermal process. Determine the initial mass of the air and the final pressure of the air. Okay, isothermal. Anybody have a guess at what isothermal might mean? Constant what? Temperature. Yeah. It's a constant temperature process. Yeah, exactly. This is a new term for us, but I don't think it's going to be that hard to understand. This means constant temperature. Okay, which implies, by the way, that the temperature at the first part of the process, before the process begins, is equal to the temperature after the process has been completed. Right? That's the key thing to recognize. That's what that implies. Okay. So let me write out my ideal gas equation. My ideal gas equation says P little v equals RT. Okay, that's good. Got that one. All right. But in this case, I don't have little v. I don't have specific volume. I have actual volume, total volume, not volume per mass, right? So remember, though, it's not that hard to relate the two, specific volume and actual volume. This is a little side note here. Specific volume, right, is equal to the actual volume divided by mass, right? So how about I make a little substitution? How about I substitute that formula for specific volume into my formula here that I'm given for the ideal gas equation? Okay, sounds good. And by the way, I'm working with air, so it's good. I want to use ideal gas. So I'm going to make that substitution. If I make that substitution, I'm going to get P big V over little m equals RT, right? And obviously, I can bring the m to the other side, and I can say P big V equals MRT. And that's another form that we're going to use sometimes. It's another form we're going to use sometimes. Okay? All right. Now, we've got a process here. It goes from state 1 to state 2. What happens? It looks like the air expands. The volume gets bigger, right? Okay? Volume gets bigger. It says first to determine the initial mass of the air. Okay? All right, let's get the initial mass of the air. That would be, so what I'm going to do here is I'm going to use this equation here and try to solve this for mass. Right? So let me solve this equation for mass. That's not hard, right? mass is equal to PV over RT. Okay. So now I have to put in all my information here. I have to put in all my information here. What's my pressure? It says air at atmospheric pressure, right? So that's going to be basically 100 kilopascals, really 101. It makes you feel better, write 101. Makes you happy, write 101, but I'm going to just write 100. Okay, 100 kilopascals. Okay. What's my initial volume? What's my volume before the process, right? 0.1 meters cubed, right? Everybody see that? 0.1 meters cubed. Good. What's my R? Well, I just told you what the R was. I looked it up. If you go here, R is 0.287 kilojoules per kilogram K. Okay. And finally, what's my temperature? Whenever you see 27 degrees Celsius, that's a dead giveaway. That you probably need to convert that into Kelvin. Because remember what the temperature difference is? Temperature in Kelvin is equal to the temperature in degrees plus 273, right? So that's going to be equal to 27 plus 273, 300, right? That's easy. That's nice. So this is going to be 300 Kelvin. Why do I have to put this in Kelvin? Why can't I just plug in 27 degrees Celsius here? Because of this here, certainly, and anytime I'm going to be dividing by a temperature or multiplying by a temperature, it's going to have to be absolute. Okay? Now, you may ask yourself here, what are the units? What are the units of this sucker? I mean, you probably ought to check them, okay? Clearly, the Kelvin here in 300K cancels with this one. That's easy, right? But it doesn't look real clear, how the rest of the units are going to cancel, okay? But if you remember, just as a side note here, a kilopascal is basically equal to, remember a Pascal, that would be like a Newton per meter squared, right? That's a Pascal, so it would be a kilonewton per meter squared, multiplied by meters cubed, right? Because look at the top. The top is kilopascals times meters cubed, right? Look at the top. Kilopascals times meters cubed. So a kilonewton per meter squared times meters cubed, what's that going to be? A kilonewton meter. But what's a newton meter? A joule. So this is really a kilojoule. So yes, the top, kilopascals meters cubed, cancels with the kilojoules, and you do get your answer in kilograms. You work this all out. I don't have this number readily handy. I know the top is 10. The bottom is 0.287 multiplied by 300. So 1173? 0.1173? Yeah. Cool, we got that. That's the mass. Okay. Where do the other meters go? Kilonewtons per meter squared times meters cubed gives you kilonewton meters. Yeah, newton meter is a joule. Kilojoules canceled with the kilojoules on the bottom, and you had basically 1 over kilograms on the bottom, so 1 divided by 1 divided by kilograms equals kilograms. So it all works out. Okay, so that's the initial mass of the air. What's the final pressure of the air? Okay, this is the other thing we're going to do a lot with the ideal gas equation. What you're going to do is you're going to make kind of an assumption here. I guess it doesn't really say this, but I don't know how this could be not true. Doesn't it seem to me that the air has to be contained in this process and the mass is going to be the same before and after this process? It doesn't say anything about air going anywhere, right? It just says it's expanded, right? It's expanding. But the mass is going to be the same before and after, right? It's not like we're sneaking mass anywhere here or there, right? It's all closed. It's all closed, okay? So we're going to assume, this is an assumption we're going to do a lot, that the mass 1 equals the mass 2, okay? How does that help me? Here's how that helps me. I already have an equation for mass. PV over RT. So now, let me set that up. If mass 1 equals mass 2, I can write the following. P1 V1 over R1 T1 equals P2 V2 over R2 T2. Right? But we can simplify that. Certainly the R is for air. That doesn't change. So the R is the same on both sides of that equation. So you can cancel it. So that can be canceled. We also said this was an isothermal process, right? So the temperature is the same on both sides. So that could be canceled. So now we have a much simpler equation that says P1 V1 equals P2 V2. So I want to solve for the final pressure of the air. That's P2. So I'll just divide this by V1, V2 there. Take that out, and I've got a nice little equation for P2. All right? Basically, it's P1 times the ratio of V1 divided by V2. Well, the volume goes up by a factor of 5. Therefore, the pressure has to go down by a factor of 5. Okay? If I assume the initial pressure was 100 kPa, it's going to be basically like that times 0.1 divided by 0.5, right? So that means P2 is essentially going to be 20 kPa, right? Final pressure, 20 kPa. Okay? We're going to do this kind of relationship a lot with the ideal gas. Okay? It's going to be very common. All right. Can you see that? Chance here. Okay.
It just about works that I did it, like just messing around doing it. Just the PV for MRT.
Yep.
Said that for P equals MRT divided by 3. And I used the 0.5 and I got 20.
No, that'd be perfectly
So
fine.
it'll work that way.
Oh yeah, of course. Perfectly valid. Exactly. Not by luck, but it's by you did just a different path of algebra than I did. But you got the same answer. Yes. If you use the M that we've already calculated, you could use that calculated M and simply take PV equals MRT and divide by V and just plug in everything and bang, there you go. Exactly. Yeah, I like what you're thinking. I like that. The reason I did it this way, by the way, is just so that people could see this relationship, because we're going to do that a lot. But yeah, you're totally right. Okay, good. All right. This one I thought was kind of interesting. I don't know if this happened to you, but this happens to me sometimes. I'll get my tires pressured up to maybe, I don't know, 32 psi or something like that, 33 or something, and then the temperature will drop a lot. Like it'll be hot and it'll be fine. I won't have any issue. The temperature will get real cold, and I started my car in the morning, and I get my tire pressure thing saying, "Oh, you got low pressure." You know, it happens to be on the cold mornings, okay, that your tire pressure drops. And I thought that's kind of an interesting application of the ideal gas equation. Why does your tire pressure drop like that? So I said, calculate the final tire pressure of a tire with a temperature drop from 80 degrees to 20 degrees Fahrenheit. Okay, so maybe it got hot one day. You know how it is. You know, one day we're near 80, and the next day it's 20 degrees in the morning. That's not crazy, right? That almost happens, in January in Arkansas. And so you've got, let's say we had a 30 psi in our tires when we had 80 degrees Fahrenheit. What would be the final tire pressure? Now this time, we got a new term for us. We are going to assume an isochoric process. Okay, now that one is not one I think you'd read and go, oh, that's obvious what that is. An isochoric process means that it's constant volume. Constant volume. That's a pretty good estimation with your tires. Yeah, not much. So a little bit maybe, but it doesn't really change your actual volume inside the tire that appreciably. So we're assumed in this process that the tires pretty much, basically you're saying that the rubber in the tires is not really stretching any different between these two places, and that's roughly true. It's not much. Okay, so we're going to assume a constant volume process, which means V1 equal V2. Okay, obviously if we're looking at what's inside our tires, I think you all could agree that this assumption also would make a lot of sense, right? M1 equals M2, right? That the mass inside the tire, we hope you don't have a leak in your tire, right? We're assuming your tire is not leaking. We're assuming that the mass inside the tire at 80 degrees Fahrenheit is the same as the mass inside the tire at 20 degrees Fahrenheit. It's not leaking. You don't have a leak. Okay? You got a leak, then your pressure is going to probably drop even faster, right? Okay. So we've got these two assumptions. The one, this is not so much an assumption, it's given, but we are going to make this assumption, M1 equals M2. But I think that's a pretty valid assumption, right? We kind of need to make that assumption. All right, now let's recall the ideal gas equation. You've got P times big V equals mRT. That's what I introduced last time, right? And then we'll solve for M, right? Solve this for M. We can say M is equal to PV over RT. And since we're making the assumption that M1 equals M2, right? We're basically, since M1 equals M2, we're again saying P1 V1 over R1 T1 equals P2 V2 over R2 T2, right? But in this case, we're going to do something different because, of course, the R's are going to be the same. It's air inside your tire either case, so the R's are the same on both sides of the equation, right? But in this case, we're assuming a constant volume process. Therefore, V1 equals V2, you can also cancel that, okay? So in this case, what we're going to write with the constant volume process is P1 over T1 equals P2 over T2. Okay? Now I want to solve for that final pressure, P2. Well, I can simply manipulate that equation as follows. P1 times T2 over T1 equals P2, right? Solving for the final pressure is equal to the initial pressure times T2 over T1. So now let's fill in the numbers. Let's fill in the numbers. Yeah, and be careful with the units. Okay, with the pressure, our initial pressure is 30 psi, so I can safely, nothing wrong with writing 30 psi right there. Okay, now my temperatures. In order to properly use the ideal gas equation, I always have to use absolute temperatures. You cannot plug in the Fahrenheits. You've got to change it to Rankine. Rankine. Got to change it to Rankine. That's the only way you can use ideal gas is if you change it to absolute, which is either Kelvin or Rankine. But this time, since my numbers are in Fahrenheit, I think I might as well use Rankine. So temperature of 20 degrees Fahrenheit is what in Rankine? Well, you got to remember to add, what, 459.67, right? So the temperature is going to be 479.67 Rankine. 80 degrees Fahrenheit in Rankine, well, that's going to be 60 degrees warmer. So what's that going to be? 539.67 Rankine, right? So now we can use those numbers into our formula here, substituting T2 and T1. The final temperature is the 479.67 Rankine. The initial temperature is 539.67 Rankine. And now I can solve for my pressure, which will also be in PSI because the temperature units cancel. So I don't have that number. Somebody can do that. It's not too hard. 26.7. I don't know about you, but when my tire pressure comes in at 26.7, my monitor goes off. It'll tell me it's 27 PSI, and it'll say your tire pressure is getting kind of low. And it warns me. It happens to me all the time in the winter. It gets cold, so the dealership says, well, we like to pump them up a little more than in the winter, therefore it doesn't drop as much. So sometimes they'll do that, okay? So, yeah, that's true. That's true. It heats back up. Your pressure can get too high. But, you know, you always get a little bit of slow leak over time. So if you go a long, long time, and it's not usually too bad. So, but yeah, it can get a little too high sometimes. Yeah. So that's why when they come in the summer, they'll say, well, we like to not put them in as much in the summer, a little lower in the summer because it'll get real hot, you know. It gets real hot, then it expands a little bit, and you get a little more pressure. So, yeah. So, anyways, I thought that was kind of an interesting exercise to see how that really, to use units that some of you may be familiar with.